Hi all, and thank Jimmy for having me here. I'm Grzegorz, and I'm a PhD candidate at Autonomous Robots Law at NTU in Norway, working with Professor Kostas Alexis. Today, I want to talk about, as mentioned, two lines of work that we both come to the same idea. So it's we want to create a paradigm that which says that it's not enough for the robot to know where to go when we are talking about motion planning, especially, but it's also the robot per se needs to know what to look at. So through this talk, I will go through two papers which we recently presented at ICRA 2026, so this year, which will capture and cover the semantic inspection with autonomous robots and also active perception for navigation for robotic systems. So this set just give you a brief roadmap. So first, we'll be talking about the semantic inspection, where we design an R policy, so reinforcement learning-based policy that finds and visually covers specific objects of interest instead of mapping the whole scene or industrial environment, you can think of it. And this work was published in RAL, but then presented this year at ICRA. And the second work is about active perception, where we aim to jointly steer the motion of an actuated camera as well as the motion of the robot itself. And that was submitted and presented also at ICRA 26. So both works share the same backbone idea, one can say. So everything runs from onboard sensing alone, so we don't have access to any external infrastructure. So everything runs on the robot, and also no privileged information about the environment is given to the robot. So the robot needs to either perform the inspection in unknown environment or perform a navigation task with active sensing in this unknown environment. So starting with the semantic inspection, so to give you an idea what it's about. So classic exploration coverage planners try to first map everything in a scene or in a let's say a limited environment, which ends up being a slow and resource heavy because you need to map first everything, and you don't really care what is really important for inspection. So real inspection missions care more about specific objects. You can think of industrial objects like pipes, tanks, cracks, whatever, like any kind of industrial object that you think that the human inspector needs to go and visually check if the system is still operational. And therefore, there is no need of mapping all the environment. We just can focus on specific objects. So the goal became to build policies which know what to look at and also how to look at it, such that the mission time can be reduced and entire performance can be more efficient than the classical approaches. So how we do that? So everything that the policy sees comes from onboard sensing. So first, starting with the depth image, which is masked by a semantic segmentation image. That's what you see in the bottom. So the segmentation image gives us or gives the network information which pixels belong to the target class of the object that we want to inspect, such that it can find it in the environment and then perform inspection. Then we also provide the state of the robot, which is the position, orientation, and its linear and angular velocities to provide smooth motion or to be able to learn smooth motions. And lastly, we provide also egocentric occupancy grid and visit score grid, which allows agent to remember where it has already been. So based on those two maps, it can navigate such that it knows where, if I have been here, as well as it knows where is the occupied region such that I will not collide with it. So those all are given to the agent to provide as observation along with the previous action. So what is important here to mention, all those observations are coming from onboard sensors. There is no external localization nor pre-built maps. So that's really important to mention. So then we train this end-to-end inside the simulator. So there are two really important design choices that we made for this to generalize well, especially for the real-world deployments. So first is the reward, which we kept quite minimal and simplistic, such that it's easy to follow and also understand for the robot what to optimize for. So first, it's a face mesh coverage term, which to differentiate which parts of the object were already covered and which are still not observed. Then we have a voxel visit score map, so VT here, which encourage the agent to find any viewpoints for inspection. And lastly, the PT term, which cares for, it's like a collision penalty, which cares for safe motion. And then second important design choice was to train entirely on the primitive shapes. As you see in the video from time to time, we train on really primitive shapes like boxes, cylinders, and spheres entirely in the simulation. Nothing which is sense specific later for the deployment. And the idea behind that was quite simple. If the policy can learn to inspect a cylinder, it should also generalize to anything roughly cylinder shape in the real world, like a pipe or a tank you can think of. And this leads us to actual deployment after training in the policy. So the policy is trained purely in the simulator on those primitive shapes. And then we dropped it into real scenarios like here. So first is the inspection of this spherical light chamber, where the policy finds in a known space the robot, like the agent or the robot here finds the object to inspect, which is then found by this segmented depth image, which is now highlighted. And based on that, and also based on those two other maps, it tries to fill the coverage up to 100% such that the whole surface will be covered. What is, as again, worth to mention, like everything is processed on board without any information of the environment beforehand. So all the map that you see also in the left bottom corner, it is online map built alongside the mission. Once the drones finishes the coverage, the time threshold, we exceed the time threshold, and then we process to the next mission. And also we show it for more than just one simple object inspection. Here in more industrial settings, we perform multiple semantic targets mission in one go. So we start with the red pipe, which will be highlighted in a second, and then the robot will continue to the blue barrel and finishing with the yellow hydrant. So what is again worth it to mention here, no prior knowledge about this environment. Robot detects based on the segmentation mask the objects which needs to be inspected. After exceeding a time threshold, it switches the mask to the next objects and looks for them in the environment, finds them, inspects. Once the time threshold is exceeded, it changes to the next object in a row. And we depict also those surface coverage plots in the bottom left corner. These are processed, we obtain them in a post-processing after the mission. So after completing the mission, we build the meshes of the objects, and then we are able to run those coverage metrics here. And within this, we show that with unseen real semantics, we can get on average around 96% of the coverage. And a full multi-object mission that I just presented to you, like pipe, then barrel, and the hydrant, takes about 157 seconds end to end, which makes it way more efficient than the standard classical approaches, which will involve first robot to explore the unknown environment, map the objects, and then perform the inspection. Here we just skip the mapping part. We just jump directly to the inspection, allowing us to reduce the mission time significantly. And quite importantly, this also involves zero environmental specific tuning, which means we can deploy the policy in any environment without any kind of parameter tuning, which is not the case for classical methods. Also, we compare the method, our proposed method, with the SOTA baseline, so classical approaches in simulation studies, getting around 95% coverage with far less inspection time. That's what I already mentioned. So with no prior per environment fine-tuning and also way less inspection time. So we with this purely inspection learning-based method, we are able to reduce the mission time quite significantly. Also, the code paper and the video I linked here. If you want to dig into details more, feel free and go ahead. But then I will also jump already to the next part of the talk, which is about this active perception. So what we observe also during while working on the on the inspection part, it's important how the policy chooses the viewpoints. Sometimes part of the objects cannot be covered with the just fixed forward-facing cameras, and sometimes you need to adjust the camera with respect to the robot to better cover objects. And we also did one step backwards and didn't apply this idea for inspection. We first evaluated and deployed for slightly simpler task, which was the autonomous navigation task. And these days, most of the approaches, especially RL navigation policies, assumes that the camera is rigidly mounted to this to the robot here, the drone will be presenting, and with that, the robot can only seize what is straight ahead of it, and it's complete. Or one can assume if there is no memory involved, then it's blind to anything that is just outside of the first room. So we ask here the question, what if the camera could move too with respect to the robot? So the robot navigates, but also independently, as with humans also navigate, we also moving our gazes all around and also rotate our heads while navigating from A to B. So why robot should also be doing the same? And then it's not about just deciding not just where to fly, but also where to look. So the payoff is quite obvious: safer flight and more richer situational awareness, essentially for free, when we switch from this static camera to the active camera, or actuated camera to be precise. So then how it works, how we train it. Also end-to-end in the simulation, we provide the robot with this first or observation, which are quite similar to what we saw in the inspection case. So the robot stayed, but now we don't have the position of the robot with respect to the world, but we have the position with respect to the goal, denoted here by G. But then we also extend it with the camera orientation. So the robot should also have a feedback where the camera is currently pointing. Then we have similarly the depth image and the local occupancy grid. How it is built along the window of depth images. We can create those local grid map, occupancy grid map, which will inform the robot if there is some occupied region that the robot might collide against, such that it also ensures safe flight during the mission or during the navigation. So how does the policy works? We trained end-to-end in simulation, and then the policy outputs six-dimensional action vector, which composed of a velocity, linear velocity, so 3D XYZ velocities, and the yaw rate, which are defining the navigation action terms. And then we also add now the pitch and yaw set points for the actuated camera to where the agent should point camera towards. So both actions are commanded by a single network, trained, as mentioned, end-to-end. So the perception control or camera control never comes at the expense of safety or goal-reaching behavior, which is quite important. So the interesting part is not really the network per se, but how we train it to achieve this motion. So the reward which guides this behavior consists of four terms, namely goal progress, which rewards the agents to get towards the goal, here depicted in the green dot. Smoothness, which is penalizes the jerky motion of the camera as well as of the agent. And this is the most important part now, is this information game. So you see the depth camera frustum on the left. So we reward the agent based on the voxels that flipped from unknown to known in the privilege information which we have in the simulator. Therefore, that's what actually drives camera to look around proactively rather than just focus on the goal. And finally, the collision penalty, which pushes the robot away from the nearby occupied space, similarly as we had for the inspection. So just to show you how it flies in real world, we deployed on highly cluttered corridor environment where some of the gaps are almost as small as the two times robot size. So there's really not so much space to navigate in. And then also here we present the camera orientation, like the camera oriented, not really dependent on the robot motion. So on the left, we depict the camera angle histograms, pitch and yaw, which vary along the mission. increasing the awareness of the robot such that it doesn't collide with the object, although they are not currently in the field of view because they were able to, like the robot was able to see them before. Next, it's another example in the T-shaped corridor where the camera moves around to increase again this situational awareness to find the gaps in the environment where the robot can pass and go through, while again trying to reach the target. So the moving of the camera doesn't compromise the navigation success or performance in general, which is not the case for the static camera policies, which will be shown in a second, where the robot truly have forward-facing camera, and then the navigation performance is decreased quite a lot. So in this setting, since the gap is quite narrow, the static camera policy fails here. So we make the environment way less challenging, where the robot then is able to navigate. It ends up in the really erratic motions you can see compared to the actuated camera policy, and also in the mid-flight collision, as indicated right now. So we show with it that active perception allows us safe flight as well as better awareness about the robot's surroundings. So that's like the very first takeaway from this work. Second is, as mentioned, safer flight. With actuated camera, we can anticipate obstacle way faster and also point camera to the regions that are right now directly outside of the flight path. But it might happen that in the future the robot will take this path, and therefore the agent already anticipated those regions beforehand with the camera, and we validate the approach quite extensively within SIM as well as in the real world experiments, and compare with the static fixed forward-facing cameras, where we show that with active perception, the robot is able to build way more richer spatial awareness compared to the static camera approaches. Again, the code, video, and the paper links or QR codes. You can go ahead and scan and go a little bit more deeper here, because as mentioned, I will just briefly cover those two works. But now you can also ask about why we just want to reward the agent based on purely voxel-based information gain. And this is like a little bit a follow-up that we are going to present in IROS this year. So if you are going to be in IROS, you can also catch up with us and have a chat. We replace those, let's say, purely naive voxel-based information gain with a signal which comes more, or is that comes from the human attention models. So humans bring priors attention and semantics to where we as humans, we are looking. So if we are navigating, let's say, corridor, there are parts of the environment that we as humans anticipate more than, let's say, a straight or empty floor or straight corridor. So we built here a GazeLNN, which is a lightweight liquid neural network that predicts human-like fixation scan paths. Live on board, so we can also feed them as a prediction to the robot camera policy that I just presented. The advantage of it is that it's quite tiny, with 0.61 GFLOPS and about 99% lighter than the next best model. Also, since it's so light, we were able to run it on the NVIDIA Jetson Orin, which within 6.84 milliseconds for one inference step. Therefore, we were allowed to do a navigation task with this model. And also, we perform simulation tests on the dataset, where we also got new state-of-the-art results, like just pointing out here to scan match score of 0.47. This was, as mentioned, a joint work with my colleague Fatma, and this paper will be presented in IROS this year, so in almost 2 months from now. And that to give you some kind of idea how it looks like. So we here mark with the colored voxels, like green, blue, and red, the regions that the GazeLNN produces. And we clearly see that there's regions within the environment that we as humans would care way more than just simple mapping of everything and rotating the camera all around. So with this work, we were able to show that while we navigate from A to B, we can give the robot more human-like behavior where the camera will fixate on the points that's predicted to be like a gaze scan of points. So just to sum up what I just presented, there are three main takeaways from this talk, I think. So first is the local onboard sensing and the way how we formulate the problems allow us to generalize well across various environments and also on various systems. So we trained the semantic inspection policy on primitive shapes, but then on the we were able to apply it directly on the real unseen industrial structures without a need of fine tuning of those policies. On the other hand, the next quite important takeaway here is that the active perception improves in general robot awareness, and that's what we get almost for free. So we just need to make the camera to move independently with the robot, and then by jointly learning camera control, we can, with the navigation of the robot, the agent is able to capture more of the environment without hurting the navigation performance. And lastly, the human attention models can be run on board and provide more human-like camera behavior for robots, which is then we can give some more human-like behavior to the robot while using active perception. So put all those together, it's not just about where the robot goes from A to B or if it's inspecting one object, but it's also the way how it chooses to look at the way. So with that, that's everything from my side. So if you're interested, all contact information are here. And thanks for listening and happy to take any questions.